This is Introductory Nuclear Physics for undergraduates and graduate students. And today's talk is about the radioactivity, in particular alpha decay. We have already gone through the initials of alpha decay, and today we will discuss more about the alpha particles emitted from an excited or unstable nucleus. I am Dr. Nasir Majid Mirza, and I will be discussing this. We have already gone through the Geiger-Nuttall rule for alpha particles, and it states that the log of lambda is proportional to the energy of the alpha particle. So the decay constant and the kinetic energy of alpha particle, if seen and plotted, then we see that the energy of the alpha particle as a function of the decay constant varies in proportion, and A and B are constants. Geiger's Nuttall law also relates the decay constant of radioactive isotopes with energy and the half-life with the energy. So rule is that the short-lived nuclei emit more energetic alpha particles than the long-lived ones. So probability that alpha will be penetrating a barrier on its approach depends on the transmission coefficient, and the transmission coefficient multiplied by the frequency with which alpha particle approaches a barrier is equal to this decay constant, and the frequency with which the alpha particles approach is given by this velocity divided by the diameter of the nucleus, or twice the radius. And then we come to know that the decay constant is given by T time divided by 2 times the V divided by R, and the result of the wave mechanical ideas give us that the log of T half, the half-life, is given as 1.61 times Z times the energy of the alpha particle with minus half power, and Z to 2/3 power, and a constant. Both the energy is measured in MeV, and Z is referring to the daughter nucleus. So the alpha chains that are well known in unstable isotopes for very heavy nuclei Z greater than 83, that are theoretically unstable, alpha decay occurs, and because the mass of the parent nuclei is greater than the sum of the masses of the decay products, the daughter nucleus and the alpha particle exhibit this decay. So what happens to N and Z when the nucleus is emitting alpha particle? Both are going to decrease by 2, and therefore 4 possible alpha decay chains are there, depending on whether A is 4n, 4n plus 1, 4n plus 2, or 4n plus 3, where n is an integer number. And we will see that how this dependence goes. One would like to estimate the Q value of the alpha particles, the energy in the reaction, and when the emission of alpha particle occurs, basically it is a helium nucleus which is coming from the nucleus, and the Coulomb barrier, which is twice as high as the probability of P emission, but it is very strong. So the Q values are large in general. Emission of the other nuclei do not play any role, such as fission, because an increase in the Coulomb barrier and there is a reduction in the cluster probability. The clustering has a probability. So if we use energy balance, the Q value of the decay is given as the mass of the original parent minus the mass, which is reduced mass by 2 in Z. It is a reduction of 2, and A is reduced by 4, and M mass of the alpha particle. Or in terms of the binding energies, we can write it further, and we can see that this is close to 0 for large A and Z, and larger the A, therefore the Q is favored. When we look at the energetics of the alpha decay, we see that this process is determined by the rest mass differences of the initial state and the final state. And in terms of the binding energy, we again see that it is basically the binding energy of the product, which must be large as compared with the binding energy of the original parent element, and the binding energy of the alpha particles. The positive Q value of the reaction indicates that such a decay will happen spontaneously, and the energy will be released as the kinetic energy of the product. And one example is this radium 226, and it decays by alpha emission, and we see that the mass of one atomic mass unit converted into energy is 931.478 million electron volts per c square. And if we use the atomic mass units values of the masses, we can find out that the energy gain is about 4.87 million electron volts, and therefore the alpha particle will be emitted. The question remains that once a alpha decay occurs, for example, in this polonium, if it happens and it is converted into lead and alpha particle, how the energy is distributed, the Q value is distributed among the alpha particle and the daughter element. The momentum conservation gives us the initial momentum and the final momentum, and from where we can get the velocities and then the energy conservation. And using this, we can find out the energy of the alpha particle, the Q value, which is given to the alpha particle. And in terms of the kinetic energy, this is the mass of the alpha particle plus the mass of the N divided by the mass of the N. And we can see how much the mass will go and the energy will be. If this is the Q value of the reaction, and then we can find it out that how much energy is given to the alpha as a kinetic energy, and how much energy is given to the other particle. And here we can see that if the energy is distributed in this form, majority of the energy is given to the alpha particle. You can see 7.83 is the Q value in the reaction, and we see that the energy carried by the alpha particle is 7.68. For typical alpha emitters, the recoil energy is small. The element, the daughter element, is not carrying any much energy, but the majority of the energy is carried by the alpha particle. Also, one Q value produces one energy, so monoenergetic alpha particles are observed. The quantum mechanical tunneling through a square well is basically the responsible, and George Gamow told us that originally that this is basically when alpha particle is coming out, it is basically tunneling through the square potential well. And if we look at the quantum mechanics of the square well, we see here the potential V is equal to 0 and potential V is equal to V and or V naught. And if the energy total is here, then we can write the wave functions for the region 1, 2, and 3. And here are these regions wave functions. We see that exponential or the e to the power iota times kr type functions are observed in the region 1 and also in the region 3. But in region 2, it is a decaying with e to the power kr type with a minus and plus, and one calls this incoming oscillatory function, which has a reflected amplitude of A, and the second wave function is two exponential decaying wave functions with the amplitude of B and C, and then there is a transmitted oscillatory wave function with the amplitude of D in the third part. We can find out the K and capital K in terms of the energies or the energy differences or the potentials. So the boundary conditions for the wave function and the derivative at r is equal to 0 and r is equal to L will dictate the amplitudes, and the K and multiplied by T is very, very large as compared to 1. Then the K is of the order of capital K. We get the transmission probability as this. We can see here that it is proportional to e to the power minus 2k times L, and K, capital K, is V naught minus the energy. Again, see here that the Q value, as the mass number is increased, is shown here, and we see that the shell effects are occurring in the neighborhood of this 210 to 220 region. So this effect is there for the odd even staggerings, and it is observed here. However, if we look at the increase, when the mass number is increasing, there is a trend of increase in the Q, slight increase. However, the variation is between 5 to 7, between 5 to 8 million electron volts. The Geiger-Nuttall's law states that the logarithmic behavior for the half-life, as we increase the Q, the half-life goes down. So we can see that the more energetic alpha particles are emitted, then the half-life is short. And when the low energy, relatively low energy alpha particles are emitted, then the half-life is large. So for thorium and uranium and plutonium, the half-life is rather large. And as we progress to this region where the californium and the radium and radon and the polonium isotope of 212 and thorium 218 is observed, then the life is short, and the Q value is very large. We can also see the alpha particle spectrum or the decay schemes. The alpha particle spectrum for californium, we can observe for the different channel numbers or for the alpha particle energies. We can see that there are peaks, and for one energy, one peak is observed, and with the full width at half maxima. So we can see that these are the transitions that are occurring. For example, from this state to the ground state, or from this state to the excited state, and so on. Similarly, the other transitions that are occurring for the beta decay, and then the alpha decay. But for alpha decay, one alpha decay, the one energy is observed, and therefore the spectral lines are really sharp, and with a good resolution spectroscopy, we can see the good small full width at half maximum and the sharp lines. Alpha decay also has this that the protons and the neutrons are bounded basically up to 7 million electron volts and cannot escape out of the nucleus. The emission of the bound system is more probable because there is additional binding energy available. And here is the pictorial representation of the potential well. A potential well in which the protons and the neutrons are bound. And once they are with the energies far below the zero value, they are really bounded and they are trapped. Now, any one such a system in which the two protons and the two neutrons get together and try to escape, they get this much bounded energy, and they want to get out of this state. Now, this much energy is available with them, but they will face the Coulomb barrier. The Coulomb barrier, you can see, has the height of about 21 million electron volts. So classically, the alpha particle is reflected back from the Coulomb barrier if the energy of the alpha particle is less than this height, and will remain within this confinement. However, quantum mechanics says that penetration through this Coulomb barrier is possible through the tunneling, and it will eventually penetrate out and come out. So classical approach is this, that the alpha particle cannot escape classically. If it is here, it will remain, it will bounce back and will remain within the potential. And if this is a potential well, then it is confined within the potential. And any particle which is alpha particle classically outside this will strike and will remain outside, will not be able to penetrate. So potential energy of the alpha particle, which is below the barrier, will remain a confined state. So kinetic energy of the alpha particle will dictate this, that it is capable of getting out or remain classically inside. But once we go through this quantum mechanical tunneling, we see that the particle behaving like a wave will be with this much energy. Then there is a finite probability that it will transmit through. And with the small amplitude of the transmission, it will come out and will have the wave function of alpha particle outside as well, and it can penetrate out. George Gamow, when tried to explain the polonium alpha decay, used these ideas, and had this notion that if the energy is above this ground state, the alpha particle energy, then this energy is enough that it will eventually penetrate through. So if we look at this schematics, and we go through the time independent Schrödinger wave equation, then we see these terms and the potential and the energy and the normalization condition. Then general answer for the solution in area A, B, and C. The A area is this, B area is this, and C area is this. We can find out the general solutions of for A and C. We have a similar equation for the K times this, and K is given by this, and the B region, which is the potential height and obstacle or opposing potential, which is opposing the transmission. Then we can solve these three equations and find out the similar we have already shown. Here we can see that the B part has this B1 times e to the power kx and B2 times e to the power minus kx. So one is coming in and one is going out, and there are two components available, and there is finite value of B1 and B2, therefore they will get transmitted. You can see here that this will be, this will have a non-zero value, and therefore it will be out. So in quantum mechanical tunneling, the wave function in A will either be reflected or transmitted through the potential, and in region C, the wave function will only travel to the right, and C2 will be equal to 0. And with the equation for with the 5 unknowns we have, we can find out the reflection coefficient and the transmission coefficient. And the transmission coefficient is given by the C1 squared divided by A1 squared, the amplitude squares. And at the position x is equal to minus A, and similarly x is equal to plus A, we can find out the values. So the transmission coefficient is, if it is non-zero and it has certain value, then it is important to guess that the quantum mechanical tunneling will take place. At position x is equal to plus A, the balance will be such that we can find out the transmission coefficient, and transmission coefficient is roughly given by this. Approximately, it is equal to e to the power times this, which has two important things: V0 minus E multiplied by L, where L is the width of the potential. So larger the width, the smaller will be the probability of the transmission, and the smaller this difference, V0 minus E, the more transmission probability will be there. So these are the controlling parameters. So quantum mechanical tunneling is possible with the transmission probability, and the exact solution for the transmission probability can be obtained with a simple box. But for more realistic potential, one has to use this kind of delta x widths and small steps, and then we can approximate and find out the e to the power with this integral. Once again, we can see from xi to xa, we can find out again the dependence is on V0 minus E and L, or 2L. The Geiger-Nuttall law, which is a relationship between half-life and the energy of the alpha particle, is given by this, and the decay probability basically is governed by the probability that alpha particle is formed inside the nucleus, and then the frequency of alpha particle hitting the Coulomb barrier, and P is the further probability, where the V is the velocity and R is the nuclear radius, and we can find out this omega, the frequency of alpha particle hitting the Coulomb barrier. It is roughly 2 to the power 21 times per second. And the P is the probability of tunneling, and it is proportional to e to the power minus 2g, where g is the gamma factor, and once we substitute all that, we get the natural log of lambda is equal to this, or proportional to 1 over under root e to the power alpha. So we can see ourselves if we plot under root of energy of the alpha particle and the wavelength, we will see a relationship, and we will have a slope, negative slope. Let's see for the experimental results. We have this log of t half on one side in years, and under root of E alpha. On the other side, E alpha is here, 1 over under root of E alpha is here, and we see a graph like this going down, which means that the log of t half is proportional to 1 over under root of E alpha, and it has a negative slope. So alpha decay obeys Geiger Nuttall's law, which states that once you increase the energy of the alpha particles, the half-life is going to sharply change. And the larger the value, the smaller will be the half-life. So, which means that the decay is such that if particles are decaying with the large energies, then those isotopes will have the short life. So, all in all, we can sum up the alpha decay theory as this diagram is clearly indicating that we have a nuclear potential well and the Coulomb barrier. And if the energy of the total energy of the alpha particle is here with the green line, dotted line, then the alpha particle altogether in totality will form an oscillatory wave function in the region 1 and a decaying function in region 2, and again an oscillatory wave function in region 3. This decaying function will have the boundary values and therefore will form the transmission and the reflection. So the transmission coefficient will be the ratio, which will be going out as compared to coming back. So that transmission coefficient will be a function of the width of the potential, this much, where the Coulomb barrier is showing itself, and then it will be also a function of the difference of the potential or the energy which is being carried by the alpha particle. So therefore, the responsible forces that are dictating the alpha decay are these two. The larger the amount of the alpha energy, or the smaller the width of the potential offered, then this oscillatory wave function will get transmitted eventually to the outside. And although it is a bounded state, it will eventually find itself out with a finite probability. Here we stop with the alpha decay theory, and we will move further towards the beta decay in coming lecture. And thank you so much.